Hi everyone, today we will be looking at current and charge. My name is Ali-Ayman and I am an electrical and electronics engineering student. I will start by explaining all the main current and charge concepts and then going over some practice questions at the end. The learning objectives for this video will be to know how electric components are shown in circuit diagrams, know the difference between a battery and a cell, understand what determines the size of an electric current, be able to calculate the size of an electric current, the time taken, or the electric charge using the necessary formula by substituting the given values into it. So let's make a start then. Let's begin by looking at electronic component symbols and how to represent them. So starting with indicators. Here is the component symbol for an indicator. An indicator such as a bulb is designed to emit light when a current passes through it. The most prominent example of an indicator is a light bulb. And here is a representation of an indicator in an electric circuit. Now let's look at cells and batteries. Here is the component symbol for a cell and for a battery. A battery consists of two or more cells. As can be seen here, this battery consists of two cells. A battery can have more than two cells, by the way. The plus sign on the cell or the battery symbol means that this is the positive terminal of the cell. So the other side must be the negative terminal. And we'll look at that in more detail. A cell is necessary to push electrons around a complete circuit. This happens because electrons enter the cell or battery through the positive terminal where they gain energy from the chemical energy stores of the cell or battery. The electrons then transfer this energy to the components in the circuit they pass through. Here is a representation of a cell in an electric circuit, and you would just replace the cell with a battery to show a battery in the circuit instead. Here is the component symbol for a wire. Wires are flexible strands of insulated metal. They are great conductors of electricity because they have free-moving electrons in their metal strands, so the electrons in the circuit can move through the wires. I will show you a more accurate diagram representation when we look at resistance, hence why they are used to connect different electrical components in a circuit. Another reason they are used is the fact that they don't overheat since they have outer insulation. And here's a representation of a wire in an electric circuit. Make sure you draw your wires as straight lines, not as squiggly lines. Now let's look at switches. Here is the component symbol for an open switch and for a closed switch. A switch enables the current in a circuit to be switched on or off. Switching on or off usually must be done manually. When the switch is open, as can be seen here, no current passes through the circuit. And when the switch is closed, a current can pass through the circuit. And here is a representation of a switch in an electric current. So when this switch is open, as it is here, no current will flow through the circuit, so this indicator will not light up. If the switch is closed, a current will flow through the circuit, and this indicator will light up. Now let's look at diodes. Here is the component symbol for a diode. A diode allows the current to flow in one direction only. The direction is also known as the forward direction. If the direction of the current is reversed or the diode is connected the wrong way around, no current will flow. And this is because the electrical resistance in what's known as the reverse direction is almost infinite, so no current can pass through. And here's a representation of a diode in an electric circuit. Now let's look at LEDs or light emitting diodes. Here is the component symbol for an LED. An LED is a diode which emits light when a current passes through it. Since it's also a diode, the current can flow through the diode in one direction only. And this is for the same reasons as a normal diode, i.e. the resistance in the reverse direction is almost infinite. And here is a representation of a light emitting diode in an electric circuit. Now let's look at ammeters. Here is the component symbol for an ammeter. An ammeter is used to measure the size of an electric current in a circuit. If the ammeter is connected to a circuit like the one opposite, which is this one here, it measures the total current in the circuit. And if the wires branch out, the ammeter measures the current through only one of the branches, the one it's connected to. And this is a reference to circuit rules, which we will look at in an upcoming video soon. And this is a representation of an ammeter in an electric circuit. Now let's look at voltmeters. Here is the component symbol for a voltmeter. A voltmeter is designed to measure the potential difference, which is also known as voltage, in a circuit. If the voltmeter is connected to a circuit like the one opposite, it measures the potential difference between 2 points, in this case across the indicator. If the wires branch out, the voltmeter measures the total potential difference in the circuit. And this is also referring to circuit rules, and we'll look at this in upcoming videos. This is typically how a voltmeter is connected to an electric circuit. Now let's look at fixed resistors. Here is the component symbol for a fixed resistor. A fixed resistor limits the current in a circuit. If the circuit arrangement is like the one shown opposite, the greater the resistance, the lower the current in the circuit, and the lower the resistance, the greater the current in the circuit. The greater the resistance, so you can increase the resistance either by adding more resistors or using resistors with a greater resistance. But in any case, the greater the resistance, the lower the current in the circuit. And in this case, the dimmer the indicator will be because less current will pass through it. The lower the resistance, the greater the current in the circuit, and the brighter the current will be because the more current passes through it. And again, you can lower the resistance by using fewer resistors or using resistors with lower resistance. However, if the wires branch out like this, more complex rules apply. And this is a representation of a fixed resistor in an electric circuit. Now let's look at variable resistors. Here is the component symbol for a variable resistor. A variable resistor allows the current in a circuit to be varied, and it does this by allowing its own resistance to be varied. So you can manually adjust the resistor on the variable resistor itself. Just like a fixed resistor, it can limit the current in a circuit. If the circuit arrangement is like the one shown opposite, to increase the brightness, you would have to lower the resistance of the variable resistor, and to decrease the brightness, you would have to increase the resistance of the variable resistor. And this is a representation of a variable resistor in an electric circuit. Now let's look at fuses. Here's the component symbol for a fuse. A fuse is a piece of metal designed to melt and then break the circuit if the current passing through it is greater than a certain amount. Once the fuse has melted, it breaks the circuit by cutting the wire and therefore prevents a current from passing through. And here's a representation of a fuse in an electric circuit. So if the current is too great, the fuse will melt and then cut the wire, and that breaks the circuit. Fuses are used to prevent accidents like fires. Now let's look at heaters. Here's the component symbol for a heater. A heater is designed to transfer the energy from an electric current to heat the surroundings. It does this by converting the electrical energy stores of the cell or battery it's connected to its thermal energy stores, which are then dissipated to the surroundings. And here's a representation of a heater in an electric circuit. Now let's look at current and charge. So what is an electric current? The general definition of an electric current is the rate of flow of electric charge, which also means the flow of charge per unit time. Per unit time and rate mean the same thing. Charged particles like electrons and ions are responsible for carrying a charge. This is because electrons have a certain property known as a negative charge, and ions can be either positively or negatively charged. Each electron carries a negative charge around the circuit. Ions can also carry a charge around the circuit. It can be positive or negative, depending on whether we have a positive ion or a negative ion. But they carry their charge around a different kind of circuit, and it usually consists of a cell connected to 2 electrodes in a salt solution. We will look at this in an upcoming chemistry series. So the greater the number of electrons that pass through a component each second, the greater the current across the component, because the greater the rate of flow of charge. When a cell is connected to a bulb, like shown opposite, millions of electrons pass through the torch bulb and through the cell every second. The electrons can move around the circuit because they gain energy from the chemical energy stores of the cell or battery upon entering the cell or battery, as we said before. The direction of a current matters. A current always flows from the positive terminal to the negative terminal. Though it appears to be moving from negative to positive, always consider the direction at the cell or battery itself, as can be seen in this diagram. The electrons move from positive to negative. And these blue circles represent the electrons. The electrons obviously have to pass through all the components in the circuit after one full turn. Now let's look at how we would do some electric current calculations. Here is the formula for electric current. Electric charge is measured in coulombs. The unit symbol is C. The equation symbol is Q, as can be seen opposite. Current is measured in amperes. The unit symbol is A and the equation symbol is I. And in the context of this equation, the time is measured in seconds and the unit symbol is S and the equation symbol is T. To calculate the current, you must divide the total charge that passes through the current by the time taken, as can be seen by this equation. This formula can be rearranged using algebra, giving us two additional formulas, which are 2 and 3. These formulas can be used to calculate the current and time taken respectively. Which equation you use depends on the values of which quantities you have been given and the value of which quantity you are required to calculate. For example, if you are given the current and time, you will probably be asked to calculate the charge. And if you're given the charge and the current, you'll probably be asked to calculate the time taken. Okay, so now let's look at some practice questions. Okay, so this question says a charge of 16 coulombs passes through a bulb in 5 seconds. And the question wants us to calculate the charge through the bulb. So I would like you to pause the video and try and answer this question yourself using the equations I showed you previously. So the first thing we need to do is identify what exactly we've been given. So we've been given the charge, because charge is measured in coulombs, and we've been given the time, because time is measured in seconds. So let's go back and see which equation we need to use from the three we looked at before. So since we've been given both charge and time, we need to use this equation here. Current equals charge divided by time. So we begin by actually writing the equation, and then we substitute the charge and the time in the equation. So we get current equals 16 coulombs divided by 5 seconds. And the answer to that is 3.2 amps. So this is the final answer. So here we have question 2a, and we have part I and a part double I. So the question says the current in a certain wire is 0.35 amps, and it wants us to calculate the charge passing a point in the wire in 10 seconds and in 10 minutes. So again, pause the video and try and answer this yourself first. So this time we've been given current and time. So let's determine which equation we need to use from the three we looked at before. So if we have current and time, it would be formula 2, because we're trying to find the charge and we've been given current and time. So that's why we use formula 2. Before we start answering this question, I'll show you how to rearrange the initial equation I gave you at the start. So the initial equation was I equals Q over T. So current is the rate of flow of charge. To rearrange this equation and get it in terms of Q, we have to multiply both sides by T. So times T here, times T there. So we get IT is equal to Q, or Q equals IT. So now let's answer question 2a, part I. So let's write down the equation, Q equals IT, and substitute the current, 0.35 amps, and the time, 10 seconds. So we get Q is equal to 0.35 amps times 10 seconds, and the answer to that is 3.5 coulombs. So this is the final answer to question 2a, part I. We also need to find the charge passing through a point in the wire, but this time in 10 minutes. So the first thing we need to do is convert 10 minutes to seconds, because seconds is the unit for time in all these equations, and 10 minutes is equal to 600 seconds. So substituting 600 seconds and 0.35 amps in this equation here gives us Q equals 0.35 amps times 600 seconds, and the answer to that is 210 coulombs, and that's the final answer. Part B says, calculate the average current in a wire through which a charge of 15 coulombs passes in 5 seconds and in 100 seconds. So again, pause the video and try and answer this yourself. So in this question, we need to use the same formula we used at the start, because we've been given both the charge and the time, and we're required to calculate the current. So we need to use the standard formula I equals Q over T. So you begin by writing it down, and then we substitute 15 coulombs and 5 seconds. So I equals 15 coulombs, all divided by 5 seconds. The answer to that is 3 amps. That's the final answer to part B, I. Now for part B, double I, we need to do the same thing, but this time using 100 seconds instead of 5 seconds. We need to find the current that passes through a wire in 100 seconds instead. So using the same formula we used before, I equals 15 coulombs divided by 100 seconds. And the answer to that is 0.15 amperes, and that's the final answer to part B double I. So now let's look at question 3. Question 3 says calculate the time taken for a charge of 15 coulombs to pass through a component at a current of 5 amps. So again, pause the video and try and answer this yourself first. So this time we've been given the charge and the current. So now let's go back and see which formula we need to use to calculate the time taken. So we have been given the charge and the current, and we've been told to calculate the time taken, and so we need to use formula 3. So T equals Q over I. So before we start answering this question, let me show you how to rearrange this formula to make it in terms of T. So we start by multiplying both sides by T, and that gives us a formula we used before, which is Q equals IT. Now we need to divide both sides by I to get this equation to be in terms of T. And this gives us T equals Q over I. So to answer this question, we need to divide 15 coulombs by 5 amperes, and that gives us 3 seconds. And this is the final answer. So now for question 4, the question says draw a circuit diagram showing a cell, a diode, and a variable resistor connected in a circuit. So again, pause the video and try to draw the circuit diagram yourself first before seeing the final answer. Okay, so to draw the circuit diagram, we need to know the circuit symbols for a cell, a diode, and a variable resistor. For a cell, the circuit symbol looks like this. For a variable resistor, the circuit diagram looks like this. And then a diode looks like this. And we need to connect the circuit with wires. So this here is the circuit diagram. We have the cell, the diode, and the variable resistor connected in a circuit. So now check your answers with what I've shown. And if you got the answers correct, then good job, but please make sure you practice more. And I'll put some questions in the description so that you can practice more in your own time. So this brings us to the end of the video. I hope this video was useful and you understood how to draw different electric components as well as the basic concepts of current and charge. If you have any questions, please post them in the comments and I would be more than happy to help. You can also attempt more questions down in the video description. If you find these videos useful, don't forget to subscribe and like the video, and more videos like this are coming soon. Thank you for watching and see you all next time. Goodbye.